Hi guys, sound check.
It's fine. Looks like it works.
Yep.
Good.
Hello to everyone. Mr. Trushin, I'm sorry to interrupting you, but I have a question for a student, Andy Hu. I wrote you a message, please answer it. It's very important. Thank you. It's Naira from Study Office.
Okay, we will start in a couple of seconds. Okay, guys, I think we should start. Well, let me explain what will happen today. So I want to switch to polynomials in several variables. But before doing that, let me briefly recall why we love polynomials in one variable. The reason is really simple, because of the Euclidean division algorithm. So if we have a problem related to polynomials in one variable, we usually apply this Euclidean division algorithm and we can solve the problem effectively. Well, not every problem can be solved via this division algorithm, but a lot of problems can be solved. Well, when we switch to polynomials in several variables, we do not have such an algorithm anymore. Well, we can even prove that there is no Euclidean division algorithm when we deal with polynomials in several variables. So what do we do? Well, actually, there is some analogous procedure which is called reduction, and it leads to the notion of Grosvenor basis, and we will deal with Grosvenor basis the rest of the time. Okay. But basically, this will be some analogy for the usual Euclidean division algorithm, but in case for polynomials in several variables. So let me formally define the polynomials in several variables, and then we will switch to the reduction. Okay, so suppose F is a field. Then, well, we fix symbols x1, etc., xn. These are just symbols. So nothing meaningful, just letters on a sheet of paper. Then, a polynomial in variables x1, xn is a picture of this form. Let me write this down, and then I will explain what's going on. So k1, etc., kn are not smaller than 0. So we consider all possible products of all possible powers of x1, xn multiplied by an element a with indices k1, kn. This element belongs to the field F, and there are only finitely many non-zero summands here. So only finitely many coefficients are non-zero. So finitely many non-zero coefficients. So this picture is a polynomial in variables x1, xn. Well, for example, we may take something like this. So we fix q. So example, we fix q as the field, so just the rational numbers, and then I can generate something like this: 1 over 2 x1 cube x4 plus 3 x2 minus 7 x5 to the 8th, something like this. So this is a polynomial in variables x1, x2, x3, x4, x5. Okay, so we have the usual rules to multiply and add the polynomials, so I believe I can skip the rules, so they're exactly the same as you use in calculus. But now two polynomials are equal if and only if their coefficients are the same. So you don't need to substitute anything instead of the variables. You just compare them coefficient-wise. The main difference with the case of the polynomial in one variable, you don't have an easy notion for the leading monomial here, because it's unclear how to compare all of these summations. Okay, but there is a notion of a total degree. So what is the total degree? So if you're given a monomial like this, the total degree of this monomial is just the sum of all the powers of the variables. That's just the notion of the total degree for a monomial. And if you have a polynomial, then the total degree of a polynomial is just the maximum of all the degrees of all monomials. So let me write it like this: for all monomials m, where m appears in F, which means that in this sum, the corresponding monomial has a non-zero coefficient. So you just take all the monomials with non-zero coefficients, compute the degree of each monomial, and then take the maximum. For example, here, the degree of this guy is 4, the degree of this guy is 1, the degree of this guy is 8. So the maximum is 8, so the total degree of this polynomial is 8. And as usual, this definition doesn't work if the polynomial f is 0, well, because there is no monomials in it. In this case, we just define the total degree by minus infinity. So the degree of the total degree of the 0 polynomial is just minus infinity. Exactly. So this is exactly the same as in the case of one variable. And we have the usual rule: the degree of a product is just the sum of the total degree of each factor. I'm not going to bother you with proving this. It's just the proof is exactly the same as in the case of one variable. And only one remark: if minus infinity appears on the right as at least one summand, then the result is minus infinity. So minus infinity plus something is always minus infinity. So this is the rule you should apply on the right hand side when you add two summands. Okay, so these are just some basic definitions regarding the polynomials. Are there any questions related to this? Okay, so now what I want to discuss, well, if we are given a polynomial in one variable, there is a very simple way to choose the highest possible monomial in this polynomial. Well, you just do it by considering a monomial of the highest degree. But in this case, when we are given a polynomial in several variables, the total degree is not enough. For example, when we consider something like x plus y, then the degree of the first term is 1, and the degree of the second term is 1. So who is the highest? It's unclear. So so I want to address this problem, and in order to solve it, I need a notion of a monomial ordering. There are a lot of different monomial orderings, but I'm going to focus on a specific class of monomial orderings, the lexicographical orderings. Well, why? Because it makes everything simpler, and we don't need to do everything in full generality. So I hope it will be much easier to understand some specific examples than go to the most general case. So the monomial orderings. We will always assume that we're given some field F. Oh, by the way, I just forgot to define one specific notation, but I'll do it just right now. So we will define the set of all polynomials in variables x1, xn as this. F x1, xn in these square brackets. So this set of all polynomials in variables x1, xn is a commutative ring with respect to the addition and multiplication of polynomials. So, okay, now I want to define a lexicographical order on the set of monomials, not polynomials, but just monomials. Okay, in order to define a lexicographical ordering, first, I need to order the variables, and then each ordering of the variables x1, xn gives me a unique lexicographical order. So, okay, the definition. So first, I need to fix some ordering of the variables. So fix and ordering of variables x1, xn. For example, we may take x1 is greater than x2, x greater than etc., x greater than xn. This is like a default ordering. But this is not the only one. You can take the opposite one, or you can take any permutation of the variables. So any ordering is valid. So, but this is the first thing we need to do. Now, when we fixed an order of variables, we can define a lexicographical order. Let me define it like this. So I will denote it like this: x1, x2, etc., xn. So here the order of the variables is exactly the same as we fixed here. So if I choose a different ordering here, they will appear in a different order here. So the lexicographical order with respect to this ordering of variables. So what is this? This is a comparison rule. So this is an algorithm how to compare two monomials in variables x1, xn. So in order to define this guy, I have to explain you how to compare a pair of monomials. So okay, suppose we're given a pair of monomials, x1 to the k1, x2 to the k2, etc., xn to the kn. And also we're given a different, not necessarily different, but an other monomial, x1 to the m1, x2 to the m2, etc., xn to the mn. And now I want to compare them. So how do I compare? First of all, I order all the variables inside each monomial in the order I fixed here. So x1 is chosen to be first. So it must be the first variable in this expression. Then x2 goes second. So x2 also must be second in this expression, etc. So for example, if I choose a different order, like xn, xn minus 1, etc., then xn should be first, xn minus 1 should be second, and so on. So the ordering here is exactly the same as here. Now, in order to compare these polynomials, I go through the following procedure. First of all, I look at the first power. So here it's k1 and m1. So I need to compare k1 and m1. There are three options. Well, if k1 is strictly smaller than m1, then I define the first monomial is to be strictly smaller than the second one. If k1 is strictly larger than m1, I define the first monomial to be strictly larger than the second one. And there is the third option, k1 is equal to m1. In this case, I switch to the second pair of degrees. So I compare, in this case, I compare k2 and m2. And again, if k2 is smaller than m2, I define the first monomial to be strictly smaller than m2. If k2 is strictly larger than m2, I define the first monomial strictly larger than the second one. And if they are the same, I switch to the next pair of degrees, k3 and m3, etc. So this is how, and then I can proceed in a similar way. And at the end, either I determine that this monomial or this monomial is greater than the other one, or all the degrees will be the same. Are there any questions regarding this procedure? Should I repeat? Okay.
No.
Okay, so let me just summarize one thing. So the first monomial is strictly larger than the second one. So let me write it here. So x1 to the k1, etc., xn to the kn is strictly larger than x1 to the m1, etc., xn to the mn, if and only if there exists an index j such that k1 equals m1, etc., kj minus 1 equals mj minus 1, and kj is strictly larger than mj. So this is the criterion for the first monomial to be larger than the second one. And as an example, if I take, let's say, polynomials with rational coefficients in three variables, x, y, and z, then, well, there are 6 possible orderings of the variables. For example, x strictly larger than y strictly larger than z. This defines me the lexicographical order lex of x, y, z. And now I can consider something like this: x squared z, x, y cubed, and x, z to the 5th. And with respect to this ordering, x squared z is strictly larger than x, y cubed, because we compare the first power, the power of the first variable x, and here it's 2, here it's 1, so it says that this must be greater than the second one. In the second case, the power, when we consider this guy with this one, the power of x is exactly the same here and here. Then we can compare the power of y, but here the power of y is 3, and here the power of y is 0. So the second one is strictly larger than the third one. So we don't care about the degree of the next variables. This is how it works. Okay. Now I want to explain several basic properties of the lexicographical order. I'll formulate this as a remark. So suppose we have monomials in n variables. Well, let's say we have this polynomial, and we fix, and we're given some lexicographical order. So we don't care about the ordering of the variables. I just take any ordering of the variables, and then I consider the corresponding lexicographical order with respect to this ordering of the variables. So here we have like n factorial options. So the first property, the monomial 1 is strictly smaller than any other monomial if m is not equal to 1. Well, this is just any monomial in n variables, any monomial. Well, this is similar by definition. So that's why it's remark and not a claim. The second thing, if we have two monomials and monomial m prime divides m, that is m is equal to m prime times t. So all these guys are just monomials. So this monomial, this is monomial, and this is also a monomial. Then m prime is not less than, m is not less than m prime, and if t is not equal to 1, then m is strictly greater than m prime. And the last property, if we have three monomials and m is not less than t, then after multiplying by any other monomial, we will get exactly the same inequality. So here m, t, and s are any monomials. So if we have this comparison between m and t, then after multiplication by any other monomial, the comparison stays exactly the same. And if we have a strict inequality, then here we also have a strict inequality. So these are some properties of the lexicographical order. Just in case, should I prove these properties, or it's clear? Are there any questions?
Seems to be clear.
Again?
Seems to be clear.
Okay, so it follows immediately from the definition, but it's worth to mention them. So, I mean, there is a natural order on the set of monomials. So the order of division. So we may say that m prime is smaller than m if m prime divides m. But this order is not linear. It's not a total ordering. In this sense, the lexicographical order is a more subtle order than the order given by division. So you may think of it as we're given this natural order, and then we make it linear by extending to the lexicographical order. So this is how you should think of it. Okay. Now I want to prove the main result about lexicographical ordering, lexicographical order. Okay, the claim. Like everything is based on this claim. So suppose F is a field. We consider the ring of polynomials in n variables, x1, xn, and we're given some lexicographical order. Some lexicographical order. So we don't care about the order of the variables. Now, suppose that m1, m2, etc. is a strictly descending chain of monomials. So these guys are monomials. So the claim is that this chain must be finite. Then this chain is finite. So there is no infinite, strictly descending chain of monomials. So if you start from a monomial, consider something smaller than it, then something strictly smaller than it, then something strictly smaller than it. Then at some point, you'll have no options. You must stop. So this is the claim. Are there any questions regarding this statement? Like, should I clarify the statement of the claim?
Does it imply that basically any descending chain should be finite?
Yes, every descending chain is finite, but the length of the chain could be of any length. It could be any number. Okay, so let me prove the claim. Well, so suppose the contrary holds. So oh, by the way, before proving this, let me explain one trick here. So I told you that we're given some lexicographical order. It means that we fix an order on the set of variables and then consider the corresponding lexicographical order. But then we can change the names of the variables such that the highest variable is renamed to be x1. The second highest variable is renamed to be x2, etc. So this gives you some permutation of variables, but after this permutation, you may think that the lexicographical order you're given is just this one. So up to changing the name of the variables, you may always assume that the order you're given is this. So I will also rename the variables in such a way that our order is this one. This just simplifies all the indices I will use. So we may assume that this is our order. Now, suppose that the contrary holds, and we have an infinite descending chain of monomials. Okay, let's take a look at the chain. So, for example, we have something like that. M1 is, let me write this down, and then I will explain all the notation. So here, K1, K2, Kn, so the lower index denote the index of the variable. And this number in brackets will denote the index of the monomial. So this is the monomial M1. Then when we go to M2, we have x1 to the K1, 2, x2 to the K2, 2, etc. xn. So let me write these for a couple of steps. Okay, but now we know that this monomial is strictly smaller than the first one. So by definition, we have two options. So first of all, I want to consider only the first column here. I want to take a look at the first variable, and actually I want to compare their degrees. So if K1 of 1 were smaller than K1 of 2, then by definition of the lexicographical order, M1 would be smaller than M2. But this is not the case. M1 is strictly larger than M2. So we have only two options for these two powers. Either they are the same, or this power is strictly larger than this one. So in any case, the power are compared in this way. So similarly, if we consider the next monomial, so we have exactly the same comparison for the powers. So the powers of x1 must go in a descending order. But now, these guys are just natural numbers. So it's impossible to have an infinite descending chain, strictly descending chain of integer numbers. So there is a number R1, so there must exist a number R1 such that when I consider all monomials starting from MR1, their degree here becomes the same. So let me write it like this. So when we consider all the monomials after this guy, the first degree must be exactly the same. And so the degree doesn't change when we consider all polynomials here after this guy. So now, if all these guys are the same, then the result of comparison depends only on this part of the monomials. So now, starting from this point, I will consider the degree of x2. And in a similar way, this is a descending chain, or at least not increasing chain of natural numbers. So again, we have this comparison between the degrees of x2, and there must exist a number R2 such that for all polynomials from the step R2, so R2 is not less than R1. So starting from this guy, all the degrees of x2 are exactly the same. So here, so let me denote it just by k1, the common degree here. And here, so we have some decreasing chain, but after this number, kn of R2, the degrees do not change. So when we consider like the next one, R2 plus 1, xn, kn, R2 plus 1. So here we have equality, and also here we have equality for the degrees. And the equality holds for the rest of the monomials. So after this step, the first and the second variable have the same degree for each number of the monomial. So again, as in the previous case, we switch to the third variable and repeat this process. Finally, at the nth step, we'll find the number Rn such that all powers of all variables are the same. So for every number I greater than Rn, all the monomials Mi have exactly the same degree in each variable. So they must have the form. But this is impossible because we have a strictly descending chain. But if all the powers are the same, all these monomials are the same, so the chain is not strictly descending. So this is a contradiction, and the contradiction completes the proof. So let me show you the whole process again. So again, so what's going on here? So we assume that we have this strictly descending chain of monomials, and then we first consider the first variable and compare the degrees of the first variable. Since this is a descending, not increasing chain of natural numbers, then at some point, all these numbers are the same. So the first degree of, so the degree of the first variable will be the same since this moment. After this moment, we consider the second variable and consider its degree. So it's also a non-increasing chain of natural numbers. So then it also must stabilize at some point. So after this moment, the first variable and the second variable have the same, exactly the same degree on all steps. Then we switch to the third variable stabilize its degree, then we switch to the fourth variable, stabilize its degree, and so on. And after n steps, we find that all monomials with index larger than some number Rn are exactly the same. So after this step, the chain cannot be strictly descending. And that's it. Are there any questions regarding the proof? Okay, but now I want to make a warning. The fact that there is no strictly descending chain doesn't mean that for any monomial there are only finitely many monomials strictly smaller than the given one. So let me clarify the remark. So I want to consider the polynomials into variables and the lexicographical order with respect to this ordering of the variables. Then if I take x squared y, then there are infinitely many monomials strictly smaller than this guy. Let me show you. For example, any monomial of the form x y to the n is strictly smaller than this guy. And there are infinitely many of these ones. You see, because we compare it first by the power of x, and here the power of x is strictly larger than here. So this guy is strictly larger than here. And it works for any power n. Now this simply means that if you have a descending chain of monomials, it cannot go through all of these guys. But we may produce a chain of any length. For example, we may consider this. And actually, we may even go further and construct something like this. So you see, this is a finite descending chain of monomials into variables, but we can control the length of this chain. It depends on n and m. It's something like n plus some constant. So the length of a descending chain may be arbitrarily large, like take n and m to be like 1 million, then the length of this chain is at least 2 million. Okay, so now we're ready to discuss the reduction. By the way, before discussing the reduction, so let me recall the way we divide polynomials in one variable. So if we are given a polynomial, say x cubed plus x, and we want to divide it by x squared plus 1, let's say x squared plus x, what do? We order all the monomials here in decreasing order. So we write all the monomials in decreasing order. Then we take the highest possible degree, the highest possible term here, the highest possible term here, and we multiply this guy by some power of x in such a way that the result will be the leading term here. So here it should be x, and after multiplication we have this x cubed plus x squared, and then we subtract, and the result will be minus x squared plus x. So you see here I use the order on the powers of x. I write them in a decreasing order. I choose the highest possible guy here. I multiply it by some other power of x and subtract from the guy on the left. So in order to simulate, in order to repeat the procedure, in order to find a similar procedure in case of polynomials in several variables, we have to fix some order on the monomials. Then we have this notion of leading monomial, and then we should repeat the procedure similar to this one. Okay, so, but let's do one step at a time. Reduction. So I will fix a field. I will consider the ring of polynomials in n variables, and I will fix a lexicographical order. It's just some lexicographical order. Now, if I'm given a polynomial f, then I can write it in the following form: c1 m1 plus c2 m2 plus etc. plus ck mk, where ci are just coefficients from the field f, and mi are monomials of the form and here I assume that m1 is strictly larger than m2, is strictly larger than m3, etc. is strictly larger than mk. So I can always write each polynomial in such a way because I have a way to compare my monomials. Okay, in this case, I have a special name for this guy. So the highest possible monomial multiplied by the corresponding coefficient is denoted by t of f, and it's called the leading term. This is the leading term. Sorry, leading term. Okay, the coefficient c1 is called the leading coefficient. So this guy is denoted by c of f, and this is the leading coefficient. And m1 is called the leading monomial and is denoted by m of f. Okay, and there is a special name for this part. It's called the tail of f. Well, I will denote it by f0. So f0, this is the red part of this polynomial, and this is the tail. So each polynomial has a uniquely determined leading term and a tail, and the leading term consists of the leading coefficient and the leading monomial. Okay, so just in case, we know how to compare monomials, but we do not have a way to compare monomial times coefficient, and we don't know yet how to compare the polynomials itself. So, well, I'm not going to discuss the way how to compare the polynomial. There is a way, but I think it's better to avoid an introduction of this definition. It's quite complicated and rather confusing. So, okay, this is the terminology I want to use. Now, suppose, so now I want to define two things. The first thing is an elementary reduction, and the second thing will be a reduction. So the first definition is an elementary reduction. So what is an elementary reduction? So we're given a polynomial f, and we're given a non-zero polynomial g. The second one must be non-zero. Why? Because we want to have a leading term in g. So now suppose there is a monomial m in f divisible by the leading monomial of g. such that leading monomial of G divides M. Then we can do this thing. We take F and we subtract the following expression. Oh, by the way, I didn't, before doing that, I should, oops, I'm sorry, it divides M. So let me write this explicitly. So F equals C1 M1 plus etc. plus some Cm plus etc. plus Ck Mk. So we have this monomial of F, and the corresponding coefficient is C. So what I want to do, I want to replace M by the tail of the polynomial G. So what I do is this. I take F and I subtract C divided by C of G times M divided by M of G times G. And I will denote the result by F prime. So this process, getting F prime from F by this procedure, is called an elementary reduction. I will demonstrate this on example in a second, but I just want to introduce a notation. So in this case, we write this. This means that we get F prime from F reducing by G. So this is an elementary reduction of F by G, and the result is F prime. Or we reduce F with respect to G and get F prime. So let me show you an example how it works. An example. So suppose we have something like this, and the order is the usual one, where x is higher than y. Well, let's say we have x, y to the fifth. Let's say x cubed y plus x y to the 4 plus 3. This is a polynomial f, and let's say 2 here. And we have a polynomial g, which is x y cubed minus 1. Then the leading coefficient of g is this, the leading monomial is this. So m of g is x y cubed. Now we have a monomial in f, which is divisible by the leading monomial of g. I highlighted it by red here. So our m in this case is x y to the 4th. Now what I do, I take f and I subtract g multiplied by 1. I want to cancel this term by this guy. In order to cancel this term, I should multiply by y first, and y is actually, and y is what was m divided by m of g. And also, I have to multiply by the corresponding coefficient 2. So this comes from here, and these two guys give me this one. And when I subtract, the result will be, first of all, x cubed y. This is the first term here. And after I subtract this polynomial from this one, this term becomes 2y, and the remaining 3 is here. So this is the new term which I will get after the elementary reduction. Okay, so this is the elementary reduction. So we need not to reduce the highest possible term. We can reduce any term inside the polynomial f by the leading term of divisible by the leading term of the polynomial g. And this is how it works. Are there any questions so far? Is it clear what's going on here? Okay, no questions. I hope it's because it's clear. Well, now I want to define the reduction. Okay, so an elementary reduction will be an elementary block for a reduction. So this is just like one step for the division algorithm. And now I can do this reduction multiple times, and this elementary reduction multiple times, and it leads to the notion of a reduction. But the difference here is that I can reduce a polynomial f by a set of polynomials. So the interesting part here is that I will divide a polynomial by a family of polynomials. So reduction, the definition. Well, suppose I have a polynomial f and a set of non-zero polynomials. And let's say I have two polynomials, f and f prime. I will say that f is reducible to f prime by g if there is a family of elementary reductions, if there is a family of elementary reductions of this form. Let me write this down, and then I will explain everything what's written here. Oops. So here, the elements gi are polynomials from G. So again, I will say that f is reducible to f prime by G, or with respect to G, or via G. These are all the same terms. So it's reducible to f prime by G if there exists a finite number of steps such that I can get f prime from f using elementary reductions by some polynomials of G. For example, I start from f. I find some polynomial in G and make one elementary reduction of f by G1, get some f1. Then I find probably the same or maybe a different polynomial in G and do a second elementary reduction. Then I find another polynomial in G and do a third elementary reduction, and so on. And after k steps, I will get fk, which is exactly the same as f prime. So this means that f is reducible to f prime. And I will denote this by this symbol. So f is reducible to f prime by g. Just in case, these polynomials need not be distinct. For example, G2 could be exactly the same as G1. That's the first remark. The second remark, this process need not be unique. So there could be different sequence of elementary reductions leading to exactly the same polynomial f prime. So this process is not unique in any way, shape, or form. And also, when I write an elementary reduction, well, it's actually the elementary reduction is also not unique, because here I do not specify the monomial in f I reduced by the polynomial gy. So I mean, even in this case, it's obscure what exactly was reduced in f. Just so this is just some warning. So here we have a lot of options. Okay. Well, now yeah. So probably I should give you an example. Well, let me do this. Well, sounds okay. Yeah. Well, I think instead of giving you an example, I'll give you a second definition. Well, oh no, let me give you a couple of remarks. First of all, it may happen that some polynomial is not reducible by the set G at all. This will be an analog of the remainder. And what could we do? We could start with a given polynomial f and start this sequence of elementary reductions, and at some finite step, the result will be a remainder. So the result will be an irreducible, non-reducible polynomial with respect to G. And what is unclear here is it possible that every such procedure leads to a non-reducible polynomial after a finite amount of steps? Or probably there is an infinite sequence of reductions. So the first problem to address is to prove that every sequence of elementary reductions stabilizes. So there is no infinite sequence of elementary reductions. That's the first problem. And the second problem, okay, if I start with a polynomial f, I can reduce it in one way and I can get some remainder, and I can reduce it in the other way and get another remainder. Well, are these reminders the same? Well, it may happen that the reminders could be different. So let me show you several. So, okay, so now the definition. So if f is a polynomial here such that you cannot reduce it by any, and G is a set of polynomials, and you cannot reduce f by any polynomial in G. Well, this means that any monomial m in f is not divisible by leading monomials of polynomials from G. Then f is called a remainder. Now, if we are given, now a remark, if we are given a polynomial f, we may reduce it in one way and get some remainder 1. Or we may reduce it in a different way probably it requires a different amount of steps, we will get a remainder 2. So it may happen that these two reminders are different. And here is an example. Here is an example. I'll take polynomials in 3 variables, x, y, and z. And the lexicographical order will be with respect to this ordering of the variables, x higher than y, y higher than z. Well, f is x, y, z. G1 is x, y minus 1. G2 is y, z minus 1. And the set G consists of G1 and G2. Now, I can reduce f by, let me reduce f by G1. So It means that I take x, y, z, and I should subtract x, y minus 1, multiply. So here the leading monomial is this one. So it appears here. So in order to cancel the term x, y, z, I have to multiply it by z, and the result will be z. And z is not divisible by the leading monomials. Let me underline the leading monomials here. So z is not divisible by the leading monomials, so this is a remainder R1. Now I can reduce f by the polynomial g2, x, y, z minus yz minus 1. So the leading term here is yz. It appears here. So in order to cancel x, y, z, I should multiply it by x, and the result will be x. So this is our second reminder.
Can you please show the definition of elementary reduction? Maybe I missed something.
Elementary reduction.
Just shortly again, the definition.
Let me show you the definition of elementary. So we choose, I can show you simultaneously the definition and the process we did here. So we should choose a monomial in the polynomial f. So here polynomial f consists of one monomial only. Then, but this monomial must satisfy this property. The monomial must be divisible by the leading monomial of the polynomial g. So in the first case, g is g1. This is the polynomial g1, and the leading term is xy. And this monomial is divisible by xy. Then what we do, we multiply our polynomial g by a coefficient and a monomial in such a way that the leading monomial of the product coincides with m, and the leading coefficient of the product coincides with c. So here we multiply xy by z such that the leading monomial of this guy is xyz, is exactly the same as this one. And the leading coefficient here is 1, is exactly the same as here. And after we subtract from this guy this product, we will get the element z. Okay? This was just an elementary reduction. Okay, so well, in general, we may need to repeat the process here. So if z were not well, if z were reducible with respect to g1 or g2, we would proceed further, and after a finite amount of steps, we will get a reminder. But here, on the first step, we will get a reminder z. And similarly, reducing by g2, we get a different reminder, which is x. Well, and it's clear that x and z are two different variables. So it's possible that two different reduction procedures lead to two different reminders. And this is the main example, how it happens. Well, the problem why this happens is actually because the set G was not good enough. Well, if the set G were good enough, we wouldn't have this problem. And this leads us to the notion of a Grosvenor basis. A Grosvenor basis is a set of polynomials G1, etc., Gn, Gk, such that every polynomial has a unique remainder with respect to this set G. So let me formulate this. Oh, I should. Okay, let me write the definition down here. So the definition. Well, again, we have a set G of polynomials, of non-zero polynomials here. We say that G is a Grosvenor basis. It's written like this because it's a German surname. Actually, Buchberger didn't invent, Grosvenor didn't invent Grosvenor basis. basis. His student Buchberger invented them, and he called them after the name of his teacher. So that's how it happened. Okay, so G is called a Grobner basis if for every polynomial every polynomial has a unique remainder, has a unique remainder, which means that if you consider any sequence of reductions, they lead to exactly the same polynomial every time you make a reduction. Well, now we don't have a tool to check if a set is a Grobner basis or not. Well, we will do it on the next lecture, but just in case, there are actually a lot of Grobner bases, and there is an effective way to check if a set is a Grobner basis or not, and there is an effective way of constructing a Grobner basis for any set of polynomials. So it's not a rare case to meet a Grobner basis. But a Grobner basis is just a good family of polynomials such that the division is good in the sense that the remainder for each polynomial is exactly the same. So if we are given a Grobner basis, we may divide each polynomial with respect to this Grobner basis, and the procedure is very similar to the one in the case of one variable. So we can also deal with reminders and solve similar problems using these reminders. Okay, so the second problem is to show that, oh, I have 13 minutes. Okay, let me think. It's probably not a good idea to start proving the second main result, so I will, okay, but I'll start.
An example of a Grobner basis.
An example for a Grobner basis? Okay, that's a good question. Example. Okay, first of all, if we're given a set G consisting of one polynomial, it's always a Grobner basis. So non-zero polynomial. This is a Grobner basis, GB. So if you have just one polynomial, then the remainder is uniquely determined. Another example, if you have, well, okay, let me give you a specific example. Let's say Q of X, Y, Z, W, then something like, and the order with respect to this, then xy minus 1 and zw minus 1. This is an example of a Grobner basis. This is also a Grobner basis. Here you see the leading monomials are coprime, so they do not have a common factor.
Remainders are polynomials that are not reducible by any polynomial in G, yeah?
Yeah, exactly. So this is exactly, it works exactly the same as in the case of polynomials in one variable. What is a remainder with respect to a polynomial in one variable? It's a polynomial which is not divisible by a given polynomial. I mean, the quotient is 0. So you have only a remainder. So you cannot make a step in the process of division. So this is exactly the same here. Yeah, so this is an example of a Grobner basis. So you can always take a set of polynomials with coprime leading monomials, and they will always form a Grobner basis. Well, we don't know how to check this yet, but we will see why this at the end of the next lecture, why this happens. Okay, now the second problem I want to address here is why the division algorithm always stops. So in general, if we have a polynomial and a set, well, actually here this set need not be finite, but we will deal with finite sets only. But just in case, I do not assume that the set G is finite. It could be infinite set. It doesn't matter. The reduction doesn't depend on the cardinality of the set. But what's interesting is you may want to make some division process, like you reduce f by g1, then by g2, then by g3, etc. And the question is whether this process stops. Does it stop? And the answer is yes. So the process always stops. And I want to make, so we don't have enough time to prove it today, but we have like 10 minutes, and I want to prove some some auxiliary result required to prove the main one. Okay, claim. Well, suppose you have you have a polynomial f and a polynomial f prime and a polynomial g in f x1 xn. Well, I assume that that f is a field and we're given some lexicographical ordering. So if we do not have any order on monomials, you cannot discuss all these notions. All these notions depend highly on the notion of the order of the monomials. And suppose that f is reducible to f prime by g. So f prime is just an elementary reduction of f by g. And suppose, I'm sorry, I forgot to introduce you an additional notation. I have to give you a definition first.
But sorry, what if g's are like? What if g is a constant? I guess any polynomial is reducible by a constant.
Yes, yes, exactly. Because every monomial is divisible by the constant, so you can multiply it and reduce to 0 every term of a polynomial. Yes, you're right, exactly.
But then how should it stop? What if there's infinite sequence of constants?
No. So you reduce a constant by constant in one step. So by definition, okay, let me show you example. So for example, your polynomial f is something like xy plus 1, and the polynomial g is, I would say, 2, okay?
Yeah.
So then the leading monomial of g is 1. So this is the leading monomial. 1, consider it as a empty product of variables, and 2 is the leading coefficient. Now, both terms here are divisible by the leading monomial. So this guy is divisible by the leading monomial, and this guy is divisible by the leading monomial. So I need two reductions to reduce f to 0 by g. So the first reduction is this. I will reduce it by g, xy plus 1 minus 2 times 1. So first I would like to reduce xy. Well, I multiply this guy by xy and multiply it by 1/2. So using this reduction, I cancel this guy. So the result will be just 1. And now I can reduce 1 by the polynomial g. So what I do, I should the monomial here is 1, and the monomial here is 1. So I do not need to multiply by any monomial, but I just multiply by 1 over 2, and the result is 0. So this is how it works in case of a constant
Yeah,
polynomial.
but then can we like reduce 0 to 0 again, or?
Oh, okay. 0 polynomial doesn't have a monomial. There is no monomials in the 0 polynomial. So
I see. Yeah, that makes sense. Yeah, sure, no problem.
okay, I see why the question appeared. Okay, yeah. So somehow you think of the 0 polynomial as an empty polynomial. It doesn't contain any monomials. So yeah, that's how you should think of it. Okay, yeah, so now the definition. So if you have a polynomial, again, you can represent it in this form. Oops. Where Ci are coefficients and Mi are monomials. I order them, I write them in a descending order. Then I want to introduce this notation. So the kth highest monomial of f is just mk. So the first highest monomial is m1, the second highest monomial is m2, the third highest monomial is m3, etc. Well, of course, this is not defined for k, k here and there. I used exactly the same k in 2 different places. Let's say I. Okay, so ith highest monomial of the polynomial f, and if I is strictly greater than k, then the left-hand side is not defined. So it's defined only if the polynomial f contains at least I monomials. But I will use this notation later. So m1 is just the leading monomial of f. Okay, so also you can define the ith coefficient. So Ci of f is Ci, and Ti of f is Ci times Mi. So this is the ith coefficient and the ith term.
Can I ask another question about reduction, please?
Yep, no problem.
Am I right that every reduction, like in a sense, just cancels out one of monomials?
Yes, you just replace a monomial by the tail of the polynomial g multiplied by some monomial and coefficient.
Yeah, thanks.
Yeah, so you just reduce one term at a time. But you have a freedom, like you may reduce this guy and then this one, or you may reduce this one and then this one. And after you make a step of reduction, you cancel this monomial, but you will get some new ones. And then you can cancel something from this set of new monomials or something that you already had in your initial polynomial. So you have a lot of options. This is how it works. Okay, well, I think it's not worth rushing here. So we'll have plenty of time to prove all the results during the next lecture and the final lecture. So we have 2 lectures from 2 lectures more. I don't think it's a good idea to formulate a new claim now. So if you have, so we have like 1 minute. So if you have any questions, please ask. So let me show you. So let me summarize what happened here. So we consider the ring of polynomials in several variables. Then we fixed a lexicographical order, and it allows us to order monomials of any polynomial So we define like it defines a leading term in any polynomial and a tail, and using this we define a procedure which is analogous to the procedure of division when we deal with polynomials in one variable. And this procedure works as follows: we find some monomial in a polynomial f, which is divisible by a leading monomial of some other polynomial g, and then we cancel this monomial by the leading monomial of g, multiplying it by corresponding monomial and the coefficient to cancel the result. So, and then after this procedure, the f prime doesn't contain this summand, but it contains the tail of g multiplied by this factor. So there are some new monomials here, but these monomials are strictly smaller than this one. And this is the process called elementary reduction. And if we combine several elementary reductions, we will get what's called reduction. And if we apply the elementary reduction, well, several times, at the end we will get some polynomials which is not reducible by our polynomials from the set G, and this is called a remainder. So the process is very similar to the one we have in the case of polynomials in one variable. Okay. That's it for today. Thank you, guys, and I'll see you next time.